So if you watched the latter videos of Chapter 6, you heard me allude to these notions of activity as influenced by the ionic strength of a solution, or really the concentration of all the other ions in solution. And so up to this point in your scientific career, you've probably only considered equilibrium and kinetics from the perspective of a pure reaction occurring in solution, and you negated any effects, any additional effects of extraneous ions in solution. By extraneous ions, I mean those that are not explicitly part of the equilibrium reaction. So just additional salt that's dissolved in water. And as I talked at the end of chapter 6 when we were thinking about solubility equilibria, even when you have other salts dissolved in solution that have no bearing on the equilibrium themselves, meaning those ions are not present in the equilibrium expression, they still have huge substantive impacts on the equilibrium reaction itself. And the reason for that is this notion of activity. So for us to understand activity of a solution or of an ion, we first need to be able to think about what is the actual form of an ion when it's dissolved in an aqueous solution. So I grabbed a video. It's not the best video, but it's pretty dramatic and interesting. This comes from a Canadian natural museum, so you'll see some French translation in there as well. And what they're going to show you is an animation that walks you through how a salt like sodium chloride actually dissolves in water. So if you throw a rock of salt, like you do if you're going to cook some pasta, into water, what's happening at the molecular and ionic level of that solution. So there's your water molecule bouncing around in solution. And there's your salt crystal, sodium chloride. So we know water molecules are polar, simply based on the asymmetric distribution of charge in the molecule. That's what polarity is. And we also know that the ions inside of a salt crystal are, the definition of an ionic solid is really an electrostatic bond. It's not a covalent bond, so electrons are not shared. They're completely given away. And so the chloride ion is negatively charged formally, and the positive charge is residing on the sodium ion. I want to be clear here, the video calls that a sodium chloride molecule. There's no such thing as a sodium chloride molecule. There's no such thing as an ionic molecule, because all you have is an infinite solid, and then all you have is ions when they dissolve. You never have a molecule as you would in a covalent compound. So that solid is vibrating, and that's true. All solids vibrate at some frequency in the solution. Those polar water molecules will orient in space to solvate, and as long as the intermolecular force from the hydrogen bond as it interacts with the actual charge on the ions, the sodium and chloride ions, as long as that's greater or a lower energy state than the actual lattice energy of the crystal that's stabilizing them in that infinite lattice, then the energy is favorable and those solid will dissolve. And what you'll end up with are a bunch of ions that are surrounded by water molecules instead of their fellow ions. And so you end up with a picture that looks like this, where negative ions are surrounded by the positive poles of water, or the hydrogens in this case. So the chloride would be on the left, and then on the right we have a sodium ion that's surrounded by the negative pole of the water molecules, the more electronegative oxygen atom. And so this is the picture I want you to think about in solution. So when we have ions in solution, those ions aren't just freely floating around. There's no such thing as free naked ions. They're always going to be associated with something, whether they're associated with themselves in an ionic lattice as the solid, or whether they're associated with the solvent, in this case the polar water, or they're associated with other ions in solution. And so in this case, in this picture, we are assuming the simplest picture, which we have done in all general chemistry courses up to this point. We just assume that these ions have a hydration sphere like this. And we assume that there are no other ions that may perturb the shape or geometry of this hydration sphere. But why is that a fair assumption? Because if we have any other ions in solution, you would imagine that the attraction to those ions would probably electrostatically be even greater than that of a polar water molecule interacting with the ion, because that's a true electrostatic interaction rather than simply this dipole ion interaction that we're seeing here. So I grabbed this picture from your textbook, and it illustrates this concept, but with a little bit more nuance. So the dark bold blue color represents the actual ionic radius of whatever that ion is, and then the light blue rings that proceed or propagate away from that blue core are what we call the hydrated radius. And the hydrated radius is exactly what you saw in the previous video. That's the shells of water molecules that affix themselves or stabilize that ion based on that ion dipole interaction with water. And you can see some trends here. So look at lithium. Lithium's this tiny, tiny ion, right, on the periodic table. It's one of the smallest cations we can have aside from a proton, from hydrogen ion itself. So you've got this tiny, tiny little core here in the center. That's lithium. And but the sphere itself is huge. Why is that? Well, you can imagine that positive one charge is localized on a tiny little sphere, so the distribution of charge per unit area over that surface area, over that sphere, is quite large relative to, say, a rubidium atom, which has the same positive one charge, right? It has exactly the same electrostatic charge, but that positive one is distributed over a much larger surface area. So the charge per unit area is quite a bit smaller. So what does that mean? Well, if you think about this polar water molecule, where the negative component, the negative pole, is going to be associated with the electronegative oxygen atom, that's going to have a much greater attraction to the lithium ion that has a much more concentrated positive charge. That charge distribution is much higher on the lithium ion compared with the rubidium ion. We can see that trend to be true over the course of all ions. And so the general association is the propensity to attract either additional ions or water molecules, or polar molecules for that matter, to the intrinsic ion is going to be a function both of the size and the charge of the ion. Of course, the greater the charge, the greater the attraction to something like a water molecule. So you can see things that have greater charges that are something like iron 3 plus has this very large hydration sphere, much larger than iron 2 plus, simply because now you have more charge distributed over the same size, right? It's a very similar argument. And of course, the size, as the size goes down, the propensity to attract water or a hydration sphere or other ions also increases. This is a fundamental idea to explaining the impacts of activity and ionic strength, or the composition of a solution in terms of other ions, on equilibrium reactions. So this is the framing. This is where we need to start in our understanding. So why does this picture matter? Well, I've got another cartoon here which I grabbed off the internet, and it has to do with what's called the ionic shielding effect. So chemistry is annoying in that we repurpose a lot of the same language and vernacular for a variety of different explanations. So you've probably learned about shielding from an electronic shielding perspective when you took Chem 107, and you probably learned about, if you took a 275 class, you also learned about shielding from the nucleus as well. Here we're talking about ionic shielding, which is a little bit different. So if we think about what's going on in solution, if you've got a positive and a negative ion, and I understand these are probably a little blurry, that was the best resolution image I could find, but if you've got a positive and negative ion in solution, so something like sodium and chloride, right, you throw that salt in solution and it starts to hydrate, meaning it starts to dissolve and you get water surrounding it. If you have a low concentration of other ions in solution, then those ions aren't really going, the other ions aren't going to really attract to it. So in other words, if you look at, say, this picture here, the orange ion right there, if you have that thing in solution, that's the negative ion, that's at the center here. Imagine that's in solution. and you've got a bunch of other stuff in solution. So maybe this is Na plus and Cl, but then you've got potassium and nitrate in solution as well. Right? The potassium and nitrate have no bearing on the KSP for the dissolution of NaCl. They're not part of that equilibrium at all, not explicitly. But what happens is as this chloride ion starts to dissolve from the sodium chloride solid, there's nothing stopping all of those negative nitrate ions from surrounding it and forming essentially a shield, because that positive negative attraction is quite high. It may not be high enough to precipitate that salt out or that ion out as, say, potassium chloride in this case, but it's high enough that the interaction is still there. And so that's what's illustrated in the picture to the left. You've got your negative ion at the core, and then the blue ions right around the periphery. You can see there's a high concentration of them. We call this the double layer often, and if you are an electrochemist like myself, we love to think about the double layer because it's about 1 to 2 nanometers thick, and all sorts of fascinating chemistry occurs right there. But the double layer is always this place where you have an ionic shielding event, where you've got your original negative ion. This is this thing right in the middle. I'm just going to color green, and that has the negative charge, that's chloride, and then surrounding that you have a bunch of positive ions, right? So what are the impacts of this shielding event? Well, at low ionic strength, meaning low concentrations of other stuff in solution, say low concentrations of KNO3, if that concentration is low but still non-zero, you do get some of this shielding, but these things can still get fairly close to each other in solution. But as the KNO3, this inert salt concentration, starts to increase, then those shielded spheres get bigger and bigger, which is what's happening on this lower picture. And what that means is the original sodium and chloride ions are further and further apart from each other. And so what we're essentially saying is that those ions, it's harder for them to get close to each other to form the precipitate, which would be NaCl solid. This is exactly what you saw in the example in chapter 6 with calcium sulfate, right? We said that when you toss in 0.1 molar KNO3 into the potassium sulfate solution where it's dissolving, what happens is you get calcium ion, and then surrounding that calcium ion are a bunch of nitrates, right, that form this nice shield, this barricade. And in doing so, those nitrates keep the sulfates, which are equally balanced by the potassiums, it keeps them quite far away. So you've got these shielded ions. The further away these ions are from each other in space, the lower the chance that they're going to go to form calcium sulfate. In other words, that's pushing the equilibrium towards dissolving more calcium sulfate, because there's less chance that calcium sulfate are going to even see each other in solution. They're completely shielded by a sheath of these other ions, these inert ions that are in solution. So this is the effect of activity. Activity is actually the method by which we can quantify this effect. In other words, how do we take something like 0.1 molar KNO3 and actually evaluate how that impacts the solubility simply based on this ionic shielding effect? That's where we need to go. So I introduced this concept for the first time in chapter 6, but I told you just to come here to get the full explanation. So activity, to understand the quantitative impacts of these other inert salts and the ion shielding and how it impacts the equilibria, we need to understand this notion of ionic strength. Ionic strength is really just a metric for how many ions are dissolved in solution in units concentration. So it really just tallies up all the ions in solution and creates a single metric. So it treats them all the same, essentially. And so the ionic strength, which we use this Greek letter mu, the lowercase letter mu, is going to be equal to half the concentration of ion 1 times its charge squared plus the concentration of ion 2 times its charge squared, etc. And so the generic relationship is just going to be the sum of all the ion concentrations multiplied by their charges squared. That's the ionic strength. So let's do a quick example. So the example says find mu, or the ionic strength, of a solution that has 0.020 molar KBr and 0.010 molar Na2SO4. So we'll write this out. So mu is going to be equal to 1/2 multiplied, and then we just need to go through the line of the individual ions. So we've got a potassium ion, we've got a bromide ion, we've got sodium ions, and we've got sulfate ions, all at different concentrations. So let's start with potassium, bromide, and work our way left to right, just logically here. So the first concentration of potassium, that's going to be 0.02. That's going to be the concentration of potassium when this dissolves, right? 0.020, and then we're going to multiply that by +1 squared, and then so this is going to be potassium, and bromide is going to be the exact same, 020 times -1 squared, so this is bromide. Then we're going to do sodium. Be careful with sodium, because when sodium sulfate dissolves, it's liberating 2 sodium ions for every 1 formula unit of the Na2SO4. So if we have a formal concentration of 0.01 of Na2SO4, we actually have a formal concentration of 0.02 molar sodium ions. So that would be 0.020 molar sodium times its charge 1 squared. So this is the sodium ion plus sulfate. And then sulfate's going to be 0.010 molar times -2 squared. So we're going to take this whole thing, and this is sulfate here. So we'll take this whole thing and compute it. Okay, so I just computed these really quick. So you can see that the formal concentration or contribution from the potassium ion is actually the same as its original concentration, 0.02. Same with bromide, same with sodium, though we're accounting for the fact that there's 2 of them that get liberated. The one that's really changes and illustrates the impacts of charge here is sulfate. Because sulfate has a -2 charge, and that goes as the square, you see the actual contribution to the overall ionic concentration, or the ionic strength, is 0.04. So we can sum this up, and if we take half of that, we get 0.050 molar as the ionic strength of the. So we think of the ionic strength of the solution really as a proxy for how many ions are dissolved at any given time, and we use that proxy then to inform the impact that those ions will have on equilibria, or in more specific terms, on their ionic shielding as it pertains to solubility and other aqueous equilibria. So as I alluded, activity then, the sort of formal definition, is a term that we're going to use instead of, or in place of, concentration. So instead of concentration as we know it, we're going to adjust the concentration value to take into account the effects of ionic shielding, and we're using mu, or ionic strength, as that metric to account for ionic shielding. I'll show you how. So the formalism for activity, at least in an expression, is that activity is really just going to be equal to the original concentration as corrected by what's called the activity coefficient, which is a constant, gamma. So we're multiplying the concentration by this value, gamma, and the activity coefficient can take on values anywhere from 0 to 1 as a function of mu. And so I'm putting here activity coefficient of C. So we're talking about some species C. That could be lead, it could be whatever it is. And then I put in parentheses here mu, because the activity coefficient here is a function of mu. And so the activity coefficient, if it's 1, right, as the activity coefficient approximates 1, then the activity and the concentration are identical, right, because the gamma here is 1. Under what conditions would that be true? Oops, I meant not here. I meant gamma equal to 1. If gamma is equal to 1, that implies that the ionic strength of the solution is 0. So, and that's really what you learned, right? All the equilibria you learned up to this point assumed the ionic strength of the solution to be 0. In doing so, you assumed the activity coefficient to be 1, which meant that the activity and the concentration were the same thing. We know that to be largely untrue, because most natural waters, most anything that you do, has other stuff besides the one reaction that you're interested in studying. There's a bunch of other stuff. And so gamma is actually not 1, because mu is greater than 0. Another way to think about it is that the gamma here, the activity coefficient, is really a proxy for the deviation of concentration from ideality. Ideality being where activity and concentration are the same thing. So the smaller gamma gets, the larger change activity is from concentration. Activity being the way the universe actually operates. Activity is essentially telling us the apparent concentration of C rather than the theoretical concentration. By apparent, I mean if you were to sort of zoom down to the molecular ionic level and look at the availability of ions in solution, activity would be a better proxy of that because it's compensating for the fact that many of those ions have been largely shielded by other ions in solution. So if we go back to our generic equilibrium reaction, A plus B equals C plus D, then we can revise our equilibrium constant from the perspective of activity. So in reality, then, the equilibrium constant is going to be the activity of C raised to the Cth coefficient here, times the activity of D raised to the coefficient D there, over the activity of A to the A and activity of B to the B. The other way to explicitly write that would be to break out each one of these activity terms in terms of its actual concentration and activity coefficient terms. So let me do that really quick. So that would look something like this, where we have the concentration of C to the Cth power, to that coefficient there, multiplied by the activity coefficient. But what's important to note is that that activity coefficient is also scaled by the same power, C. So if you've got a coefficient that balances your reaction of C, then you're not only raising your concentration as you normally would, but you're also raising your gamma value. And that makes sense because it's the entire activity coefficient that gets raised to the power C. And so we're just breaking those two things out here. And so that's true over this entire equilibrium expression. So if we look at a more substantive example here, so just looking at KSP, so the solubility of silver chloride, we can write up the KSP. That's just going to be equal to the product of the concentrations of the two ions, so silver ion and chloride ion. If we write that out in terms of the activities explicitly, that's going to be the concentration times that sort of adjustment coefficient, the activity coefficient here, for each of those individual ions. And remember that this gamma value can take on any value from 0 to 1 as a function of the ionic strength. And so as ionic strength gets bigger, let's just say ionic strength is bigger, then the gamma value, your activity coefficient, gets smaller. So what does that mean in terms of, say, like the solubility? What are the real-world implications here? Well, let's say we have a whole bunch of other stuff dissolved in the solution, let's say sodium nitrate, because neither of those ions participate in this specific reaction equilibrium. So you've got a bunch of sodium and nitrate ions in solution, say like 2 molar, high concentration, meaning we have a high ionic strength, right? Ionic strength is really high. If ionic strength is high, then the deviation from ideality is high, which means the gamma values go down. They're quite a bit smaller. And so if those values are, say, let's just make things up, 0.1 and 0.2, then the apparent concentration of silver and chloride are roughly 1/10 and 2/10 what they would be if we didn't consider activity. So that's much smaller. If the equilibrium constant is fixed, say it's 10 to the minus 6, I don't know what it actually is, if the apparent concentrations are much smaller, then that means the reaction can proceed to make more ions. It can increase the concentration of both of those ions because they're much lower than what they would be if we didn't include the gammas, right? So they're going to increase until they again satisfy whatever our KSP value has set for them. So what that's telling us, which is exactly what we found with the case of calcium sulfate in one of the chapter 6 videos, was as we add more inert salt, as the ionic strength of the solution increases, the solubility of salts also increases, which is exactly what we observed when we were talking about the definition of these things, right? When we're talking about shielding of these things, what happens is the more stuff you have in solution, the further those ions can be from each other in space, and because of that, there's effectively a lower concentration of those ions in solution. So this is the way that you should calculate all equilibria to be the most accurate in your model for reality. The other way that we use equilibrium constants or activity in this case is for this example, we can adjust our KSP value to be activity corrected. So sometimes you'll hear people talk about activity corrected KSP, or you'll look up a table where things are activity corrected, and your book shows this. So remember that KSP is an equilibrium value. All Ks are literally equilibrium constants, and those all assume, as you started to assume in general chemistry, an ionic strength of 0. But we could compute a new KSP, and we often call that KSP prime, under some specific condition where, say, mu is equal to 0.1 molar. And so your textbook has all of the equilibrium constants, at least the KSP values, computed over a few different ionic strength ranges. And the way that those are computed is exactly the way we have this set up. So if you can imagine, you've got KSP is equal to your silver ion concentration multiplied by the gamma, or the activity coefficient of silver, by chloride concentration, and then the activity coefficient of chloride. If we want to correct our KSP for whatever the mu is in the system, then what we'll do is just take KSP divided by the mu, or the gamma of silver times the gamma of chloride. So we're essentially just dividing those two components. So now we have silver plus and chloride minus, and that's going to be equal to the activity corrected KSP. So we're just dissolving in those contributions from activity, and that KSP is corrected for whatever mu those gammas were computed over. How do we compute those gammas? That's the next question. There's a couple different ways. Your textbook has a table that looks like this, where you have a whole bunch of ions on the left. So you have all the ions over here, and then these are grouped by charge. So you have all the positive, negative ones up top, the 2s and 3s and 4s as you move further down. And then you have the different ionic strengths here. And the values in the table here that are all between 0 and 1, these are all the gamma. These are the activity coefficients for those different ions. This is a nice convenient table because it doesn't require any math. And so if you're working with concentrations that are nice round numbers, like 0.1 all the way down to 0.001, then you can look into this table and grab those really quick. In this class, I like to use the Debye-Huckel equation, which is a mathematical description of gamma, of the activity coefficient, that can be computed with this expression. So 10 to the minus 0.51 z squared, z being the charge on the ion that you're trying to compute the gamma for. So say you're looking for calcium 2 plus gamma, then the charge would be 2, times the root of the mu being the ionic strength, of course, in this case. So I will always give you this expression. I use it all the time. This is an empirical expression. That's why it looks weird. It doesn't look like a very consistent function. And the reason for that is it's simply just a relationship based on experimental values. It's an empirical formula. It's not a true theoretical value. And it works pretty well. It fits data pretty well up to about 0.1 molar. And so this is a good approximation of the activity coefficient up to 0.1. If you need to go above that, and we're not going to do that in this class, there are other sets of equations that get more complicated, one of them being the Pitzer equation, and so we're not going to do that. For this class, this will always work. Just always use the Debye-Huckel equation, or you can use a table like this if you'd like. The other thing I want to draw your attention to with this table is just looking at these values of the activity coefficient. So for the smallest ion way up here, or not smallest, it's actually fairly large. It's 900 considering the hydration sphere size. At low ionic strengths, you're pretty close to ideality, almost 1, meaning there's little effect at low ionic strengths, which makes sense, right? There's not much other stuff in solution. Then our approximation is pretty consistent, where concentration and activity are about the same. But as you descend this table, where the charges go to 2s or 3s or 4s, then of course the effects of ionic shielding become really important, because if you've got an ion that's got a 4+ charge, of course any other ion with a negative charge even remotely near it is going to have a strong electrostatic interaction with it, creating a huge shielding effect. Huge shielding effect make it less available to participate in its equilibrium reactions, so essentially rendering its apparent concentration lower. And that's what you see all the way down here. If you've got these large 4+ or 4- ions, the concentrations become very, very different from the activities, simply because of their size and their charge.